Number 2. Now we're going to get into some limiting reactant and excess reactant questions here. 6.0 moles of N2 are mixed with 12.0 moles of H2. Now notice I have 2 significant figures here and then 3 significant figures here. So let's keep that in mind when we go to record our answer, report our answer, our final answer. According to the following chemical equation, notice that we have an already balanced chemical equation. And just remember, if there's no number listed in front of that species, that's a 1. So we have coefficients of 1, 3, and 2. We are being asked which chemical is in excess. In excess. So which one of these will have some left over after this reaction goes as far as it's going to go. So instead of trying to do this in your head and say, okay, well, there's 6 moles of that and 12 moles of that. There's twice as much as that. Okay, twice as much H2 as there is N2. But we need 3 times as much H2 as N2. And trying to do that in your head, don't do that, right? You're using a skill that's not necessarily practicable. In reality, it is, but we do not have any way to practice that in this course because we try to rely on the factor label method of dimensional analysis. So let's rely on that, the thing that we have practiced a lot. So we are going to take both of these quantities, 6.0 moles of N2 and 12.0 moles of H2, and we're going to set up 2 different conversion factors, and we're going to convert from each of these reactants into the single product. So I'll go ahead and set up crosshairs. I know I have to convert out of each reactant. So I'll go ahead and just set up those units so that they'll cancel out. Now, in this problem, there's only one product, so it's not really an issue. But in reactions which have more than one product, you have maybe 2 or 3 products here, you have to make sure that you always convert into the same product when you're trying to identify your limiting reactant versus your excess reactant. That way, the numbers that you generate are comparable, right? The phrase that you've probably heard is you can't compare apples and oranges because they're not the same thing. You have to make sure that you have the same unit, right? You're looking at the same product to see which reactant is actually producing less product. But like I said, in number 2, that's a non-issue because there's only one product. So whichever one of these 2 numbers ends up being less, right, less product, is going to end up indicating the limiting reactant. Because remember, the limiting reactant is the reactant that will run out, right? All of that will be gone. The reactant that would produce more, would produce more, that's the key phrase, word, would produce more, that's the one that's going to have excess left over. So let's use our mole ratio. So N2 to NH3, that's a 1 to 2 ratio. H2, that's a 3 to 2 ratio. So some simple calculations, that ends up being 12. Let's see, 24, that ends up being 24, 8. Right? Right? We can double check that in the calculator if you would like. But notice that the H2 is actually producing less product. Less product is being produced by this H2. So that means that this is limiting and N2 is in excess. Now let's make sure that we understand what the question is asking for. I'm not done. Which chemical is in excess? Well, N2 is in excess. And also there's a second question. What is the excess in moles? What is the excess in moles? Now, I do not know how much of this 6 moles of N2 are going to react. I don't right now. All I know is that some amount less than 6 moles is going to react, right? Because it's this 12 moles that are going to completely react. It's these 12 moles that are going to be completely consumed, right? So I don't know how much N2 is going to be used yet. But I do know that 12 moles of H2 will be consumed. So what I can do, and which is what is the next step, I take that 12 moles of H2 that I know will react, and I convert out of moles of H2 and into moles of that excess reactant, the N2. Now, what's the mole ratio? 1 to 3. This ends up being 4 moles of N2. I'm going off the screen a little bit there. But this means that 4 moles of N2 will react. Okay, will react. I have 6 moles. 4 moles will react. So, good old-fashioned 6 minus 4 equals 2. All right, so 2 moles, this is the second part of my answer, 2 moles of N2 will remain. 2 moles of N2 will be in excess. All right, there's a couple different ways you can phrase this second part of the question. What is the excess in moles? There are 2 moles excess N2. All right, B, theoretically, right? Not in reality, but theoretically, how many moles of NH3 will be produced? Well, we already identified that the H2 is limiting, right? So theoretically, again, not in reality, theoretically, all 12 moles are going to react. That would produce 8 moles of NH3. And so I've actually already done this calculation up here in part 8, or in part A. So I already know that my answer is 8 moles of NH3. Now, I got to use my 2 significant figures from my initial data. And if you are being a very critical listener right now, you're thinking, Johnson, there's no work here, right? You always mark me down when I don't show work. Well, simple enough. You did show your work right there. There's no need to do it again. You've already done it, right? You've already done it. Again, I said this multiple times in class. In section 1 of this chapter, we learned about the mole ratio. In section 2 of this chapter, we use the mole ratio in the factor label method of dimensional analysis, doing those stoichiometric calculations. And in section 3, we're not doing any new functions. We're just interpreting that data, right? And so that's what we're doing here. This is an interpretation of a function we can already do, right? So the answer to B is 8 moles of NH3. Again, if you want to make sure I don't knock you for, not showing your work, show me a little arrow to where your work actually is, right? That's good enough. Part C. If the percentage yield, so remember, we're looking at this. The percentage yield of NH3 is 80%. How many moles of NH3 are actually produced? So I'm actually solving for the actual. Now, just like way back when in Chapter 2 and Chapter 3, we did some algebraic rearranging of the density equation. If you guys remember, that's density equals mass divided by volume. If we were asked to solve for any of these different terms, we would simply algebraically rearrange the equation. Here, I'm being asked for this term. So I'm going to algebraically rearrange that equation to solve for actual. So in order to do that, I'm going to have to multiply both sides by the theoretical. And so what I'll end up with is actual is equal to percentage yield times the theoretical yield. Okay. Now, before I go plug in the numbers, let me point out something. I have not plugged any numbers in yet. Don't deal with the numbers until last, just like setting up your crosshairs in the factor label method of dimensional analysis. Keeping it like this simplifies your action. It makes it more simple. If you plug in your numbers, right, this number and then this number, if you plug that in before you start moving the terms around, it's very easy to forget which number represents which term and end up putting the numbers in the wrong place. What I really suggest you do, rearrange the equation with the terms in mind first, right, just like I've done. Write out the equation that solves for what you need to solve for, just like I've done here, and then continue the equation. This is equal to, and now start plugging in your numbers. Okay, 80%, right? That's the percentage yield. That's what the question told me, times the theoretical yield. Well, theoretical yield we saw in part B was 80%. Sorry, 8 moles. And now I know exactly what to do. 80% multiplied by 8 moles. So, in other words, what is 80% of 8 moles? 8.0 multiplied by, now here's the thing, that's a percentage. Yeah, that's a percentage. When you plug it into your calculator, you want it to be a decimal, right? And so you can either do in your head and say 80% is 0.8 as the decimal, or if you don't trust yourself, like I don't trust myself very often, I'll actually, too far. I'll actually put the mathematical function that would turn 80% into a decimal, which would be dividing it by 100. And I end up with a final answer of 6.4 moles. Okay. Now, what this is telling me that as a whole, this whole number 2, is that I'm mixing these two reactants together. Okay. Now, based on how much of each reactant I'm mixing together, the H2 is going to run out first. So based on this amount, the limiting reactant, 12 moles of H2, I can potentially, theoretically, if under ideal conditions, there's that term from section 2, ideal stoichiometry, ideally, I could produce 8 moles of NH3, right? Theoretically, I could produce 8 moles of NH3. Do I? No, I actually produce about 80% of that. I produce 80% of that, which is 6.4 moles. Again, actual versus theoretical.